The number of tonnes of carbon dioxide emission that we'll save from going into the atmosphere if we get to 50 gigawatts of offshore wind will be 40 million tonnes of carbon dioxide. But I want you to consider being crushed by that weight of CO2.
We are live today from the Coast Laboratory. This is the Coastal Ocean and Sediment Transport Laboratory at the University of Plymouth, and we're going to find out all about renewable energy generation out at sea and some fantastic research.
We don't have to burn the fossil fuels because all around us is a replenishable source of renewable energy. We're here today specifically to look at the types of renewable energy that we can get from the marine environment, the sea environment.
So my name's Deborah Greaves. As Natalie says, I'm Professor of Ocean Engineering here at the University of Plymouth and also the Director for the Coast Laboratory. And I'd like to welcome you and introduce you to our fantastic Coast Laboratory here at the University of Plymouth. And following on from what Adam was saying, what we do here is we like to scale down the conditions that would be experienced at sea into a laboratory controlled environment so that we can run experiments and learn how these new structures and these offshore renewable energy types actually work. We do a lot of research in offshore renewable energy, and at the moment we're leading something called the Supergen Offshore Renewable Energy Hub. There's lots of resources and information there that you might like to look into. But within offshore renewable energy, we include offshore wind, wave energy and tidal stream energy, as Adam has said. What you can see at the moment is a number of small waves being generated. We can generate waves in the wave tank of up to just under a metre wave height. So that's pretty dramatic when we have the big waves going. But not just the wave generation, we also have within this basin a current generation system that goes along the tank and another one that goes across the tank. And that means that we can recreate the conditions at the sea, including the waves and the currents. And very soon we're going to be installing a wind generation system as well, so we'll be able to have wind, wave and currents all combined together.
So Anna's working for a PhD in marine energy engineering. So Anna, tell us a little bit about your research. What are you studying?
So my research is about cables for wind turbines. So a wind turbine like this that's floating needs the electricity to be taken onto the shore so that we can use it in our homes and everything. And so the cables have to go from the wind turbine to the seabed, and they have to be able to withstand all kinds of loads from the turbine moving around and from the waves themselves. And so I'm designing those cables to work better and to make sure that they don't break, essentially, in the 25 years that they need to be there.
So Emma, Dr. Emma Edwards, she studied and obtained her PhD in marine energy, I think.
Ocean engineering.
Ocean engineering.
Yeah, that's
Tell
right.
us about your research to get your PhD and now the research you're doing here.
Yeah, so my research during my PhD was on wave energy, so converting energy from ocean waves into electricity. And what I looked at during my PhD was optimizing the shape of the wave energy converter, so how we can get more power out from changing the shape of the wave energy converter. And what I work on here at the University of Plymouth is floating offshore wind, and particularly I'm looking at this model scale floating offshore wind turbine that you see in the tank. So this is 70th scale of the 15 megawatt turbine. And I'm looking at how to model it in the lab.
So these are really big machines. I think, am I right to say they would be 230, 240 metre blade diameters, and that is the size of the blades across on one of these. And the 15 megawatts, I think you're saying about, can power 15,000 homes or 60,000 people's electricity.
Yeah, it's like,
wow, this is
it's
big.
Big scale, yeah.
This is big engineering.
This is our mini tank, which we use for demonstration of the concepts of wave energy. So you can see this one is a raft with some hinges and lots of different sections connected together. And as the wave is generated by my assistant here, then you can see the different sections are moving relative to one another. And in the hinge, if we put a power takeoff, type of power takeoff, which will convert that motion into electricity, then we can generate electricity. So this one, we've got different sections floating on the surface. And then over here you can see this is called a point absorber, and if we can get the waves to generate at just the right frequency, then the yellow part is a buoy, and you can actually see the copper coil there, and inside this column we have some magnets that you can see there. So what we've got, if we get exactly the right frequency, and this isn't playing the game for us today very well, but we should be able to see this bobbing up and down in the waves. And you can see the coil is moving through the magnetic field.
Adam has a nice demonstration of this here that he's made himself.
This was a little toy knocked up yesterday in our lab.
He's such an engineer.
And what we have are some magnets here and a coil of wire. And this is called a linear generator. And as the magnetic field passes the coil of wire, you've probably learnt about electromagnetic induction. We get electricity produced in that coil of wire, and we can see that the light-emitting diodes give us a flash as the magnets pass through the coil.
At this end, we have something called an oscillating water column. There's some air trapped inside this chamber, this glass chamber, and as the waves go up and down, it changes the volume that's available for that air, and so some of it's going to be pushed out through this duct and then drawn back in again as the wave level goes down. And you can see what's happening in this duct. We've got a turbine there. It's a unidirectional turbine, and it's spinning. And as it's spinning, we've got a generator in there, just like we would in a wind turbine, and that's lighting up the diodes. In this duct, we have a different type of turbine. And if you look very carefully there, you should be able to see that it's not stopping and starting. It's not changing direction. It's spinning in the same direction, no matter which direction the air is going. So we've still got the air going out and in, just like we did in that one, but the turbine this time is spinning in the same direction. So these can be built into seawalls, like this example here. In fact, there is one in northern Spain that's been operating for about 10 years now, I think, generating electricity to the grid. But they can also be built into offshore floating devices as well. So we've also done quite a lot of experiments with floating oscillating water columns as well.
So exciting, and there's so much engineering in here. So hopefully we're inspiring a few of you with lots of potential engineering solutions.
So living in the southwest of the UK, you probably realise that our country, the United Kingdom, is completely surrounded by water. We're actually very lucky as far as marine renewable energy resources are concerned in the UK, because we're right at the edge of the Atlantic Ocean, and we have a huge wind resource blowing onto our country, a great wave resource, and some of the best tidal resources anywhere in the whole world. But in order that we can capitalise on that, we need facilities like we've been looking at here today, so that we can design, build, make more reliable, and run the amazing engineering devices.
So thank you so much for joining us, everyone. Hope that's been really inspiring. Think about all the exciting opportunities for engineering in this area of engineering and in so many others. Thank you to our amazing engineers here, and that's it from Coast Laboratory in Plymouth. Thank you. Bye.